Hello, and welcome to section 3.6, which is about inverse functions, how to get derivatives of inverse functions, and we're going to do it using the chain rule. It's a kind of a weird section. It can get really tricky. So let's buckle in. So first of all, we're going to do the warm-ups in just a few minutes. But first, I want to review some facts about inverse functions. And there's two views I want to look at here, two ways of looking at this. So the first way of thinking about inverse functions is this, that the input and output values are swapped. So for example, if you plug in a value of a here, like 3, and you get 7, so if f of 3 is 7, that is true if and only if f inverse of 7 is 3. So you take the input and output values and switch them, and that makes it the inverse function. And that's actually the way you define a lot of functions like square roots, logarithms, inverse trig functions are kind of defined in this way. So some examples of this notation is the cube root function on the left here is the inverse function of something cubed. So if 2 cubed is 8, then you should be able to take the output from that function, make it be the input into the inverse function, and the result should be 2. So the output and input are swapped, in other words. If you do that on a graph, if you take all your xy coordinates and you swap their places, so this looks like 4, 6 or something here. That's going to correspond to this one having coordinates 6 and 4, which isn't quite accurate. I didn't draw it quite exactly, but it's what I was intending. So if you swap their xy coordinates, you end up with this, with all of them getting reflected across the graph of y equals x. The last thing we need to see here is one example of an application of this. So this is a function where you can input a temperature in degrees Celsius, and if you plug it into this function, the result, the output, will be the corresponding Fahrenheit temperature. And so, for example, if you plug in C equals 0 degrees, the freezing point of water, into this, the result will be 32 degrees Fahrenheit. So if you take that value of f and plug in f equals 32 degrees Fahrenheit, the result of this whole function operation will be the corresponding Celsius temperature. And this whole way of looking at it is actually equivalent to view number 2, which is that these are functions that cancel each other out. So if in other words, if you do a function composition with them, like f of f inverse of x, you get x. You should actually also get the same thing when you do f inverse of f of x. Whoops. You should still just get x. With either way you do it, they should always cancel each other out. So here's some examples of those properties. The function, the natural log function and the exponential function cancel each other out. You plug the output of natural log into the input of the exponential function, and the result is just the input to the exponential function. So I kind of said that in like the input and output are swapped language, but you can just use this equation, is that they cancel each other out. The same thing happens with the square root and x squared. Those functions cancel each other out. Sine and sine inverse of x cancel each other out. And I should mention there are complications to all of this. You've probably seen before when f of x isn't one-to-one, especially when you put the inverse one on the outside. So for example, if you take the square root function and compose it with x squared, you don't always get x if you plug in something negative. So, for example, if you take the square root of -3 squared, that's the same as the square root of 9, which gives you 3, which is not -3. And likewise, if you do sine of 3 pi, well, so the angle 3 pi, it means go around here 1.5 complete rotations, and the angle there is 0. So sine of 3 pi is equal to 0, but there's a lot of other angles that make sine of that angle be 0 too, and sine inverse can only be one of them. So you just get this one over here as the result. So there are complications like that. Now, we need to talk about something else before we go on to the warm-ups really quick, which is this. If you weren't here on class on Tuesday, October 3rd, you might have missed this, but I'm handing this out tomorrow. I'm actually recording this in the past. So I'm going to pass this out on Tuesday, but I'm updating the way we do homework. And the reason I want to do that is because, and I'm not changing anything very drastically here. This is just a formula, but I do want to mention my expectations for what you should be doing, especially with the video notes. So let me talk about why I wanted to do this homework update, which is that I think people were a little unsure of how much work they should be doing out of the class, but I want to break it down for you hour by hour for like a typical student. So in a traditional class, a typical student goes to the 5 hours of lecture, if it's a 5-unit class like this one, and then usually the rule for the typical student, whatever that means, is to multiply that by 2, and that's how much homework you should be doing outside of class. And that really depends a lot, both on the student and how well prepared they are and how fast they are at working, and there are all kinds of different preparation things. And it also depends on how much work they want to put in and what grade they want to get out. So for some student, like working 10 hours a week might get you a B, but if you worked 6 hours a week, you'd end up with like a C minus, just barely. And that same student might be able to work 15 hours of work a week to like really master everything to get an A. So it depends on the student, how prepared they are, and also how much time they have to put into it and the grade they want to get out. Anyway, so that's just kind of typical. So this class is different with the flipped classroom. The lecture videos should be taking up something like half of the time outside of class. The classwork is 5 hours a week, so that's like half of the practice work that you do. There's also the book homework and studying, which there isn't very much of that. I'm only assigning like 5 or 10 problems from each section, as opposed to a traditional class where I might be assigning like 15 or 25 problems per section to be doing that 10 hours of homework. So there's not really that much of this extra homework here. And so the lecture videos really should be taking the place of like 5 hours of lecture. And I think 4 or 6 hours is typical. And I'm getting that by thinking like about 1 hour to 1.5 hours per video per section. And that might be different for some sections, like section 3.4, for example, was longer than section 3.5. So anyways, it depends, but something like 4 or 6 hours per week. And for some students who are working really hard and some students who are being lazy, it will vary. So some students might be able to get by and get a C in the class, or they might already know calculus and they might be able to get by with like 2 or 3 or 4 hours on the videos, and some students might need more, depending how much time you're taking. And so these lecture videos are supposed to be part of the work in the class. And that means I really do expect people to be doing the warm-up questions and the practice problems. And on the video notes, I want to see all of that and the corrections to your work when you see the correct answers. Because I do want to know that you're spending something on the order of magnitude of something like 5 hours on per week on the video notes. If you're spending like, I don't know, 1 hour per week on the video notes, that's equivalent to spending 1 hour a week in the lecture class. And that hopefully sounds crazy. If there's a 5-hour class and you're only coming for 1 hour, you're not really going to the class at all, and you're missing most of it. So the same thing applies with the video notes. So that's a correction of the formula, so I'm going to pass this out. These are some details about how to put it together. You can ignore it for now. And on the back side, there's a new homework scores sheet with a corrected formula there. Anyways, let's get to the warm-ups. Here's the warm-up problem. These are derivatives. Practice using the chain rule because most of the section is going to be about the chain rule. So let's give these a shot and we'll see the answers in 3. And I really mean do give these a shot. If you get them wrong, I want to see your wrong answers, then cross it out when you see the right answers, and then show the work for the right answers, because this counts as essentially homework too. All right, so let's pause it in 3, 2, 1. So here's the answers to A and B, and I'm going to hold off on the answers to C and D. I want to work those out because these are really what this section is about, is kind of the method we're going to use for these problems. So let's look at A and B first. These are what I got. It's a basic sort of chain rule problem combined with some other rules, of course. The outer function is the square root, which I wrote using the 1/2 exponent notation. The derivative of that is 1/2 times the original function to the power negative 1/2. The inner function is e to the x plus 1. So that still gets plugged in. The derivative of that is just e to the x plus 0, because the derivative of the 1 is 0. So that's how that works out. This one, the outer function is 4 to a power. The derivative of 4 to a power is just 4 to that same power, but multiplied by the natural log of 4. And then I multiplied that by 2t, which is the derivative of the inner function, t squared. So that's that. Now let's look at C and D. Both of these have an easy way to do them, and there's also the hard way to do them. First, I'm going to show you the easy way. So C method 1 is just to realize that h of x here, this function, is, well, it's only defined when x is positive, by the way. If x is negative, this is undefined, because the square root of a negative number is undefined. But as long as x is positive, they just cancel out. We can say the square root essentially cancels out with x being squared, and we just get x for values of x where the original one was undefined anyways. So that's that. And then the derivative of that is just equal to 1. So that works. Then same thing with D. Here's method 1. So as long as x is positive, which is the domain of natural log, then e to that power and natural log just cancel out. So this g of x function is just x. So that means that if you take the derivative of that function, you just get 1. So that's the answer to these questions. That's method 1. But what most of the section is going to be about is the second sort of way we're going to do it using the chain rule. So method 2 for C would be to say that this is a composition of functions, this h of x function here. it's a square root on the outside, which I'll write as the power 1/2. And, oh, no, I'm sorry, it's x squared on the outside. And it's the square root on the inside. And that means we can use the chain rule with that because we have a composition of functions. So h prime of x is going to be this 2 times its input to the power 1. That's the derivative of the outer function with the original x to the power 1/2 plugged in. And then we need to multiply that by the derivative of x to the 1/2, which is 1/2 times x to the 1/2 minus 1, which is negative 1/2. And then we could simplify this a little bit. We could say there's 2 times 1/2 is that, and then we have x to the power 1/2 minus 1/2 when we combine those exponents. And anyways, the whole thing works out to just be 1. So that works. Now, how can we do D using this method 2? This might have been something you tried, by the way. This method 2 works for part C, and method 1 works for part C too. So you might have done it either of these ways. If you did it both, then you get a gold star. But you should know that both of these work. But anyways, let's see what happens if we try that with D. Just wherever I have room over here. So to do that over there, that g of x function was e to the power on the outside, and the inner function is the natural log of x. So to use a chain rule on this, the derivative of g of x is going to be, well, the derivative of e to a power, the outer function, is just e to the ln x with the original inner function plugged in, but we need to multiply this by the derivative of natural log of x. And at this point, you'd be like, I don't know what this is, because we haven't learned it yet. Or maybe you do know it because you have learned it, but congratulations. But at this point, you're kind of stuck. So the question is, we don't know that, so we're stuck here for now. Actually, we're not totally stuck, because I want to use this way of thinking to find out a formula for this. And we'll see how to do that. I brought the stuff over here so we could just see both of these in the same place. So the way we're going to find this derivative of natural log is using the fact that this function e to the power natural log of x is the same function as x. No matter what x you plug in, you get the same thing here. So if it's really the same functions, then its derivative must be the same. So whether you do g prime of x this way, or you do g prime of x this way using the chain rule, both of them are g prime. So we can say that the g prime of x from method 1 is equal to the g prime of x from method 2, because they're both legitimate rules. I didn't break any algebra rules or anything. So we can say that, and then, so the goal, remember, is to find the formula for this, and this actually gives us an equation that whichever way you write g prime of x, it has to be the same function for all values of x, so we can use that to get an equation for this thing that we want. One thing we can do to simplify it is just to cancel out the e and the natural log, because we know they're inverses anyways, so that means we can write it as 1 equals just x is what comes out of that. times this derivative, which we want to find. So to find that, I'm just going to take this and divide both sides by x to get that derivative by itself, and it cancels out, and we get 1 over x is the derivative we're looking for. So this is a method to find the derivative of natural log. So you have two options. Well, one, this is a thing you have to memorize, but it's also a good thing to be able to figure out by using this property, that you could write it either as x and get the derivative, or write it this way and get the derivative, and those two functions must be equal, and then solve the equation for the d over d of x this way. But you definitely need to know that formula. That's an important one. Okay, so that's our first way of doing this trick to find the derivative of an inverse function. This is a peek into the future. Here we are in the past again. Generally, we're going to use this fact. This fact right here is true with any old inverse functions, and we just did an example of it with the natural log, but it works with all kinds of other things too. And so let's go over a method for how to find, this shouldn't be here yet, how to find the derivative of any old inverse function for whatever your original function is. So we start with this property of all inverse functions. This is true if you have the inverse function on the inside. Remember, those complications always come up when the inverse function is on the outside. But so this is the basic property of inverse functions, and so if these two are equal, then we can take the derivative of the function on the left and of the function on the right, because they're the same function. So on the left here, we're going to have to use the chain rule because it's a function composition. Whoops. So and then on the other side, that should be equal to the derivative with respect to x of x. So on the right, this very stylishly cancels out into just the number 1, because the derivative of x is just 1. And on the left side, we have to use the chain rule, where we're going to have the derivative of the outer function, which is f prime, with the original inner function plugged in. And then we need to multiply that by the derivative of our inner function, which in this case is the derivative of f inverse of x. And remember, the whole point of this operation is to find this fraction. And this trick just gave us an equation that has that fraction in it. So that has that function, that derivative that we want in it. So we're going to divide by everything else to cancel out this stuff. F prime of f inverse of x, and do that on both sides. Whoops. Okay, there we go. And it cancels out on this side, and we just end up with an equation for the derivative that we want. And so this is an important fact to know. but it's not always clear how to apply it. It's kind of a weird equation what these different kinds of notation are, but it is a good thing to know. But there's actually, I'm going to show you, there's a way of getting around this. You could get around this actually by actually doing these things with your particular function, like we just did with the natural log and e to a power. Like if you go back to where we were right here, this thing we just did with e to the ln x, that was just f, or this is really just, we're writing x equals, the outer function was e to the power ln x. And then if you take the derivative of both sides, you get 1. That's the derivative of x. And the derivative on the other side worked out to all of this stuff. And you just divide both sides by x. Anyways, I was just trying to write it in the same way. If you start with that equation, with whatever your particular inverse function is, whether it's natural log or sine inverse or tangent inverse or whatever, you can just go through these steps using the chain rule like we did here, and it works out. And if you don't want to go through all of those steps with each function, you could just use this result. It's a good way to check that this works is to do it with the inverse function. So actually, let's do that right now. I'm sorry, I meant to say with the natural log function. So if our f function is e to the power x, then our f inverse is the natural log of x. And if we're going to follow this rule, the derivative with respect to x of this ln of x would be 1 over f prime, whoops, should be equal to 1 over f prime. Well, f prime is actually just e to a power, so that's the denominator there is e to this power, but then what we plug into it is f inverse of x. So that looks like that, and e to the power ln x is just x, so it works out this way as well. We got the same derivative for natural log of x just using the formula. So you can either know this or work out these steps for each one. Okay, so let's go on to a couple examples of how to actually do this. So there's the one way to do this with arctangent. Arctangent, by the way, is an alternative notation for tangent inverse. So the one way to do this is just using the rule. So the quick way using the rule is to just say our function f that this is an inverse of is tangent. And that means f inverse is our arctangent function. And so to use that rule, f inverse, the derivative of f inverse of x should be equal to 1 over the f prime function. So we need that right here too. So the derivative of tangent is 1 over cosine squared of x. And if we plug that in here, in the f prime place here, that's our thing here, 1 over cosine squared of x. But we're not plugging in x into it anymore. We're plugging in arctangent of x. So I lied. This isn't actually the quick way. Both ways are a little tricky here, but we'll see it works out both ways. So how do we figure out cosine squared of arctangent of x? Well, we'll look at that in a second, but first I'm just going to simplify this complex fraction and rewrite it as... So we can start by simplifying this just by multiplying both sides of this by that denominator, cosine squared of arctangent of x and this just becomes the derivative of this function arctangent of x. Let's write it out as arctangent of x is this just cancels out here and you just get this top. And then the question is how to simplify this, because this is a really ugly formula. There's two ways to think about it. One way is to draw a right triangle where arctangent of x is an angle. Because remember what this notation means. Arctangent of x is an angle with the property that sine of that angle should equal x. So let's draw a right triangle with an angle. So here's a right triangle with theta, and we need to have the sides be some length so that when you do tangent of sine of theta, what am I talking about? I'm talking about tangent of theta. Whoops. So we need to make it so that tangent of this angle is comes out to be x, which in tangent, remember, is just the opposite over the adjacent. So this triangle needs to have those sides labeled in some kind of way that makes the sides come out to be x. So one way to make that work is x over 1. You could also do 3x divided by 3 would also work, but let's just keep it simple and do x over 1 to make it so tangent of this angle becomes x. So then, what is cosine of this angle is the question. So we're going to use the Pythagorean theorem to find the hypotenuse, because cosine of this angle, the thing we're trying to find here, is the adjacent side from theta, which is 1, divided by the hypotenuse, because that's the definition of cosine. So what is a hypotenuse? You're going to have to use the Pythagorean theorem to see that this is the square root of 1 squared plus x squared. So that means that cosine of this angle is really 1 divided by the square root of 1 squared, or 1 squared is just 1. The square root of 1 plus x squared. And so that's what cosine of arctangent of x is. Then when you square that, that will cancel out with the square root here. So this will just end up being 1 over the square root of 1 plus x squared squared, which is just 1 over 1 plus x squared. That is the derivative of arctangent of x. So that's a good one to know. That's another one that you either need to memorize or be able to figure out. This one actually, I always have a hard time memorizing, but I can figure it out really quickly. I can do it in my head in, I don't know, 10 seconds or something. I could kind of write down, I might have to write down some of these steps, but yeah, I like figuring things out a lot. But you could also just memorize that one. Okay, so that is the way I was saying is the quick way. The way that's the slightly longer way is just instead of doing this step, let's write this over here. Is to just write out the f of f inverse of x equals x, but in this case we're going to do it with tangent. So tangent of arctangent of x, just based on the way inverse functions work and the definition of arctangent, this should always be equal to x. And then doing the derivative of both sides. And this is the same way, by the way, that we did the derivative of natural log, or we found the derivative of natural log, and the way we did it sort of abstractly up here. But I'm just going to work all that out one more time to see that it's really the same thing as just using that formula. So the derivative of the outer function, the derivative of tangent, is 1 over cosine squared, but with arctangent of x still plugged in, that's equal to the and then we still have to use the chain rule here. This section really is still about the chain rule. We need to multiply this by the derivative of arctangent of x, and that should be equal to the derivative of the right side, which is just 1. So that's the differentiating both sides step. And next step, we just multiply both sides by this whole thing. I'm just not actually going to write that out. Just say multiply both sides by that to bring it over, and that gets you this derivative of arctangent of x is equal to 1 times that cosine squared of arctangent of x. So and then here we still have to do the trigonometry. By the way, we should go over another way to do this step. If you don't like drawing this triangle, if this seems weird to you, you don't understand the concept, here's another way you could figure this out. A way to turn this cosine of this weird angle into tangent of this weird angle. So let's remember our most important trig identity, which is sine squared of anything plus cosine squared of the same angle is always equal to 1. I want to turn this into tangent, so I'm going to think of this as like dividing each side of this by cosine squared. And I did that because that gives us a nice tangent squared of theta function here. And so there's tangent squared of theta plus 1 is the cosine squared over cosine squared, and then 1 over cosine squared I'm just going to leave like that. And what I have is cosine squared of an angle, so I need to know what cosine squared of the angle is equal to make a substitution here. So I'm going to multiply both sides by cosine squared of theta. And then divide both sides by tangent squared of theta plus 1 so that this can cancel out. And so cosine squared of theta is equal to 1 over tangent squared theta plus 1. And that way you can also use a trig identity here to say that this is equal to 1 over tangent squared of arctangent of x plus 1. And anyways, tangent of arctangent just cancels out to be x, and then when you square that result, we just end up with x squared plus 1, which is the same thing we got before. So I want to show you there's kind of two different things you can do two ways here. There's first of all just setting up the derivative formula. First, I did it using this formula here. That was what I said was the quick way, even though it wasn't really that quick. Or you could do that setting up the f of f inverse of x equals x, canceling out formula, and then taking the derivative of that function on both sides. And then using the chain rule to get the derivative of the inner function, using that trick that the chain rule takes a derivative of that and gives you an equation with it. And then there's also the trigonometry. So there's the way to do this setting up the equation, not the equation, sorry, setting up the angle here, the triangle that has that arctangent of x angle in it, or there's this other way here of doing it with the trig identities. Whichever way works better for you is okay. Let's do one more with arcsine of x. This one, you should give it a shot. So I'm going to pause it here, and the answers will appear in 3, 2, 1. All right, so here's my answer. I got 1 over the square root of 1 minus x squared. If you got that, excellent. You got it right. If you got something else, that's okay. Cross out your old work. I still want to see your old work, and then let's write these steps down. So, and you might have done it differently too. If you use the formula from before as a little shortcut, it might look a little different. Anyways, I set up the f of f inverse of x equals x function equation like this. Then I took the derivative of each side, and taking the derivative of each side allows you to use the chain rule here, because the derivative of the outer function is just cosine of the original arcsine of x inner function. Then that needs to get multiplied by the derivative of the inner function, and that gives you this equation here that has this derivative in it that we want. So we just need to solve this equation to get a formula for the derivative of arcsine of x. So I divided both sides by all of this stuff, cosine of arcsine of x, and then there's this thing here, and cosine of arcsine of x is really ugly, so you need to simplify that somehow. So here's the way I do it using a little trigonometry knowledge. I know that arcsine of x always represents an angle, so here's a triangle with that angle in it. So sine of this angle, I set it up to be x over 1. So that much is known about the triangle if this theta is arcsine of x over 1. But then if we want to find cosine of this angle, which we need to do because this says cosine of arcsine of x. So to do cosine of this angle, we need to know this other leg. So I'm using the Pythagorean theorem with that b squared, one leg plus the other leg squared, x squared, should equal 1 squared. And then you just solve that equation for b. So b ends up being the square root of 1 minus x squared, which is where that came from. So that's another thing that's a good idea to know. If you don't know it, you should be able to figure it out. Okay, that's basically what we have in this section. I want to do a little summary here, and then I'll give you some practice problems to do. The basic idea, the thing that you need to be able to do from this section, is be able to differentiate functions involving natural log or log base b, or log whatever base you have, or sine inverse, cosine inverse, or tangent inverse. And there's 3 basic methods for this. The first method is to use that first rule. So that was just that the derivative of the inverse function is equal to 1 over f prime with the inverse function plugged in. And again, this doesn't always quite, it's not always very simple, I mean to say, because sometimes the f prime of f inverse is really complicated, like it was with those trigonometric ones. The second way is what I was doing for most of these examples, which is setting up this identity equation. It's always true if there really are inverse functions, which says that f of f inverse of x is equal to x, and then differentiate both sides. You'll need to use the chain rule to get the derivative of that f inverse out. So that's that. And the third way is just to know all of the formulas, which takes a lot of memorization. I'm going to write them all out here. So here's all those formulas. There's really these 5 of them that are the ones you will probably need to memorize. So I'll say that it's not like 3 is really an alternative for 1 and 2, because you really do probably need to know these formulas, because they're going to come up often enough that like doing all of these steps every single time for all of these derivatives is going to take too long. So you'll want to know them. Now let's do some practice problems where we'll need to use these. So this is just a little bit more derivative practice problems where you're going to have to use these formulas. Now again, you don't have to use these formulas. You could figure out the derivative of arctangent again from scratch every time. Find out the derivative of natural log again from scratch if you want. But that's probably a lot of extra work, especially when you have the formulas right here. So let's just practice using them with a few more derivatives. And let's pause it here to do the problems, because the answers to check your work will appear in 3, 2, 1. All right. So these are the answers I got. For A, I'm just using the chain rule here. So the outer function is natural log. The inner function is sine inverse. So the derivative of this outer function is just 1 divided by x, but instead of x, we're plugging sine inverse of x into it, and then times the derivative of sine inverse of x. And then using the formula for sine inverse of x, you get this. So that's that. And then for part B, same idea. It's just this time the outer function is arctangent. Now let's look at this formula to see the derivative of arctangent here. It's 1 over 1 plus x squared. But this time, instead of it being x squared, you're plugging in your e to the t for that x instead. So it's e to the power t squared. And that, oh my goodness. Okay, so just as I'm recording this video, I think it's a possum jumped out of a tree. I think it fell out of a tree and landed right next to me. I'm outside in my backyard. Alright, the possum ran away to the other side of my backyard. Oh well. Anyways, real wildlife adventures and math videos. Where were we? So, and then we need to, so the chain rule here, that's the derivative of the outer function with e to the t plugged in, times the derivative of e to the t, looks like that. So that worked out. This one's just using the product rule. There's the x over here times the derivative of the second factor plus the derivative of the x times the original second factor ln x. And that simplifies out like this. Alright, so it is way past my bedtime, so I'm going to try to upload this tonight and go to bed. And I'm going to try to avoid possums. I hope that you do too. Have a good day.